I've always found the intersection of both science and fiction to be one of the most mesmerizing forms of art. From tinkering with the delicate balance of time travel to venturing into a great unknown galaxy, anything seemed to be possible. It was in this realm where I witnessed the first African American woman, Nichelle Nichols, play the role of a space traveler in the iconic series Star Trek. As a young girl, watching someone that looked like me do extraordinary things opened my mind to what and who I could be. Years later, I found myself embarking on my own sci-fi adventure and boldly going where no man has ever gone before. Or at least no one in my family, that is. I was admitted into UNLV's neuroscience PhD program, and it wasn't until after I began my own research on the brain's ability to produce energy that I saw that the line that separated science and fiction wasn't as definitive as I'd once thought. Hi, my name is McGlothen, and today I have the pleasure of navigating us on a sci-fi adventure through the brain. Now, some of you may still be a little skeptical as to whether energy dynamics of the brain are as cool as what we may see in movies. Well, I'm here to tell you today, they are. For instance, in the 1999 film Star Wars Episode 1, they mentioned something called Mitochondrians. These were a microscopic life form that lived in symbiosis with a host, and an important component to detect the energy field known as the Force. In the film, one could actually measure the level of midichlorians within an individual to see how strong they were in using the energy field. The force, zoom, 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 is defined as an inner source of energy that powers all living things. And this is true for each one of us. Yeah, the concept of a small organelle supplying power doesn't just exist in the captivating world of Star Wars, but in the everyday life cycle of the eukaryotic cells that make up all plants and animals. Yes, ladies and gentlemen, mitochondria, the powerhouse of the cell. It's a small organelle that supplies the fuel needed to meet cellular energy demand in the brain. Disruptions in mitochondrial dynamics have been implicated in many neuroinflammatory disorders such as multiple sclerosis, ALS, or Parkinson's disease. Lack of effective treatment options highlight the need to reevaluate disease pathology in order to find novel therapeutic targets. Much of what we know about mitochondrial energy dynamics highlights the role of neurons. However, the metabolic impact of immune cells such as microglia that are that first line of defense in the brain, there's still so much to be explored. This ultimately led me to ask what exactly is happening to the energy dynamics of mitochondria inside of microglia during disease states of the brain. To measure this, I will be measuring the mitochondrial membrane potential, also known as the MMP. Now, similarly to measuring the levels of midichlorians with an individual, I have found a clever, novel way to measure the level of mitochondrial activity inside of microglia. And what I've done is used a fluorescent dye to make it happen. Essentially, I've obtained these specialized living brain slices from mice that have glowing green microglia. And what I've done is I've added on a dye that allows me to see changes in activity of the mitochondria on these slices. Next, I was able to put these slices underneath my microscope in order to take movies and at the same time introduce a toxin called LPS that creates a disease state in the brain slice. And it essentially activates these cells to move into action because they are immune cells. And the very first adventure I wanted to take was to see if there were any mitochondrial differences between neurons and microglia. So after taking a 30-minute movie, I saw increases in the MMP at 3 different time points that I'm going to refer to as states 1 through 3. And this happened after I administered that toxin LPS, and it happened more dynamically in the microglia represented in green than it did in the neurons represented in blue. I had to take a closer look at each one of these states because it was way too cool not to. Remarkably enough, the intensity of the MMP seemed to be moving at each state. The mitochondrial activity was moving from the body of the cell all the way to its fingertips, also known as end feet. When we looked at things like the rate of change of the MMP over time, we saw that there was this quicker and more intense change happening in the soma at the beginning, and a more intense change happening in the end feet, or the fingertips, towards the end. I wanted to see if there was a way to somewhat rescue these effects by adding a neuroprotective drug. And to my surprise, I was able to decrease the microglial MMP at every time point when administering a neuroprotective drug. Together, these results suggest that mitochondria may be moving from the soma all the way to the end feet during disease states of the brain, and perhaps microglia may have their own signaling processes located there. I never could have imagined that my innate love and curiosity for sci-fi adventures would have paralleled the captivating world of neuroscience. As I progressed through my graduate journey, the same feeling I once got watching space travelers maneuver the stars is the feeling that I get watching my microscope. The ultimate goal for my research is to advance the way that we understand energy metabolism and to use this knowledge to earlier diagnose inflammatory diseases of the brain. And perhaps along the way, inspire someone else to boldly go where no one else has gone, just as I once was. I'd like to thank Dr. Dustin Hines, Dr. Rochelle Hines, the Hines Group, and all of you for your time. Bye.